Welcome to another exercise for the workbook Statistics. This time we're focusing on Loglinear regression approaches. Let's have a look at the exercise. Here we have an exponential relation exists between the maximum temperature of a year in degrees Celsius, which is x, so the independent variable, and the agrarian output of this year in 1000 tons, which is y, the dependent variable, following the corresponding form. Our form here is y is equal to parameter a times e to the power of b times x. Our task now, well, using this data, we should determine a suitable, with a suitable regression approach, the parameters a and b in this equation. Well, we cannot directly use linear regression because this is not linear, so we need to use a different approach. Whenever we have a form like this, that's where Loglinear regression comes into play. Well, let's try this approach. For this, we first start with a slight reformulation of the original equation. So what we're going to do, we take this equation, the one we've been given, and we reform this by first off applying the logarithm on both sides of the equation. If we do this here, we have on the left side logarithm of y, and on the right side we have logarithm of a times e to the power bx. Well, here we can apply the rules for the logarithm. If there is a multiplication inside the logarithm, we can pull this apart, so we get logarithm of a plus logarithm of e to the power bx. Again, we can still simplify this a bit more by applying the rule of the logarithm once more, meaning here I chose the natural logarithm because this is the one which counteracts the exponential function. Meaning the last part simply is bx. And now what I'm going to do is, well, this looks linear. Here I have the dependent variable, which now is logarithmized. I have an intercept, I have a slope b, and I have my independent variable x. So I can simply recalculate first of the y, so I take the logarithm, the natural logarithm of y, and then I run a regression, a linear regression with logarithm of y as dependent and x as independent. So I'm going to do this. I'm using the data from the exercise, and I add a new column on the right where I calculate means of the respective variables I'm going to need later on. For y, I'm not yet doing this because I won't need the mean of y, but I need the mean of x. So first off, I calculate the mean of x, and then I add additional rows. The first row is actually the logarithm of y, and for this I'm calculating the mean again, because as I said, I'm running my linear regression not with y as dependent, but with logarithm of y as dependent variable. So that's where I'm going to use this one here. Then I'm going to calculate the squares of x and average them, giving me this value. And finally, I'm going to calculate x multiplied with logarithm of y. So those two giving me this, those two giving me that, and so forth. And then I'm also averaging this row, because those four values are the only thing I need to calculate the parameters for my regression. Well, how am I going to go about this? First, I'm going to calculate the slope parameter b. I can use the classical formula from linear regression, which is just x times ln of y, the average thereof. So I'm going to use this one here, the 90.2423, minus the average of x, 24.6, times the average of ln of y, which is the 3.719. The upper part, this part here, that's actually my covariance. I'm going to divide this by the variance of x, so the average of x squared, that's here the 610.2, minus the average of x, 24.6, to the power of 2. That's this part here. I'm going to put all of this in my calculator, yielding me a slope of minus 0.247. This parameter is actually the same from the original equation. But now I also need to calculate, well, first off, the intercept for my linear regression, thereby getting my parameter A for my log-linear regression or model. For the intercept part, I'm going to calculate, first off, ln of y averaged. I'm taking the 3.719 minus b times the average of x minus b, well, b is negative, so I get here plus 0.247 times the average of x, 24.6. Putting this into the calculator gives me a value of 9.7952. Here I have to take care. That's ln of a. That's not a, that's ln of a. So to get my parameter a, I have to use the exponential function on this. If I'm going to do this, my result in this case will be 17,947.3904. Those are actually the two parameters I can now put in my model for the exponential growth. That's the parameter in front, that's the one before the x variable. Well, that's everything there is to say on this exercise, so I hope you enjoyed it. And well, I say goodbye and see you next time.